Greetings, AP Calculus AB students. Mr. Record here from Avon High School, and welcome to our 8th video, more use of the chain rule in our long topic that covers one of the most important ideas in differential calculus, topic 3.1 from the CED, the chain rule. This video is going to focus more so on the exponential functions and logarithmic functions that are not in base E. And these are a lot more rare in terms of the AP exam. And sometimes we don't really see these often from year to the year. In fact, I don't know if I can recall ever seeing a logarithm of base A on the advanced placement exam for a student to differentiate. But I'd like to include them in my curriculum to give my students a full umbrella of calculus and the derivatives that they can take, as the fact that it very well could be a part of the Calculus 1 experience at the college level. So basically, if I have you turn your attention right away to the third box down, the derivatives for bases other than E, I've got this derivative formula a to the x. And by definition, the derivative of a to the x is the natural log of that a times that a to the x power. And that's really all there is to it. It doesn't involve the chain rule. I'm going to show you that version here in just a moment. But if we move down here to example 8, differentiate y equal 2 to the x power, we can see how we can easily apply that particular derivative formula and come up with natural log of 2 and then multiply by 2 to the x power, and then boom, we're done. That's all that we have to do to take that derivative. Now you might wonder, well, what about our old friend, the derivative of e to the x? Maybe you remember him. The derivative with respect to x of e to the x was just e to the x. But if you think about it, wouldn't there be an ln of e in front of him? Just like this a to the x, it looks exactly the same now, and that's exactly correct. But this ln of e, if you recall, is just equivalent to 1, so we won't really have to write it. So really we have an all-encompassing procedure or formula for taking the derivative of some base to the x power. So what would the chain rule version of this look like? Well, if we move over to the right side, the chain rule version just says, well, if you're going to take the derivative of a to the u, then you still would start with ln of a times a to the u, but you just tack on that derivative of u with respect to x. So for the purpose of part B here, the derivative of y with respect to x would be the natural log of 2, once again, starting off that way. Take our 2, but this time raised to the 3x, and then we can multiply by the derivative of 3x, which is just 3. Now, there's a variety of ways to write this too that I'd like to share with you. Perhaps the 3 could be written in front of the natural log of 2, and then we follow that up with 2 to the 3x. And then there is a dirty trick that one could do. Maybe your teacher would be so vile as to take that 3 coefficient, plant it up here in that exponent of the 2, which we know it can do, and have the natural log of 2 cubed, which is the same as the natural log of 8. Now, it's likely that that's not going to happen, but if you're working through multiple choice problems or circuits or something that is sort of self-checking, you know that, oh, well, that answer doesn't show up, that answer doesn't show up, but you're pretty sure that they're right. You might be looking for a more simplified version like we have here at the bottom. Let's finish up with our last example that's going to use the derivative of the log base a. Now the formula without the chain rule, as we can see right here over to the left, is the log base a with respect to log base a of x, derivative with respect to x, is 1 over natural log of a times x. Now, if you look at the 1 over x part, that ought to make us feel pretty good, because over here, I'm going to rewrite a really popular derivative that you may have remembered, natural log of x, and we know that he is just equivalent to 1 over x. So at least we have that common ground, the 1 over x, that's shared by the derivative of the two logs. It's just that we have to remember that this ln of a is going to appear in the bottom of that particular derivative, just like the ln of e would appear at the bottom of our derivative with natural log. The chain rule version just uses a bit of an adaptation, and we have our 1 over ln of a times u all on the bottom, just as you would expect, and then we just make sure that we multiply that by our derivative of u. So in this particular case, dy over dx would be 1 over our natural log, and 10 is our base here, and then we would keep going and write our u, which is cosine of x. All right, next up, we take the derivative of that cosine, which would be negative sine. right? I can see it right there. It's negative sign right below me, right? Derivative of cosine is negative sign. That is your answer. You could leave it like that, although it can be simplified a little bit. Sometimes when you can write one trig word instead of two, it's a bit advantageous. Sine over cosine we know is tangent. We can just lay the negative in front and then keep that natural log of 10 down in the denominator. Now, I know that this video did not go into a lot of detail about why these particular derivatives are the way they are. And if you want more insight into that, that's where the two boxes up at the top come into play. They're just relationships or definitions that you may have encountered in a pre-calculus course, but you can simply manipulate them a little bit using the chain rule to actually come up with these particular derivative formulas. Like I said, it's very likely that this one right here does not need to be memorized before the AP exam. Every once in a while, it's not been seen quite often, but the derivative of a to the x is something that's worth having your finger on to make sure that you're comfortable with him. By and large, these are going to be very rare. All right, we have only one more video to talk about with our chain rule. We're going to talk about taking derivatives in a much more conceptual way and using information from a table to answer those derivative questions, and that's coming forth in video number 9 from the series. Anyhow, we thank you for joining, and we'll see you next time.